this talk. Dolphins are cool, explosions are cool. Exploding dolphins are not cool. But cooler heads prevailed on that. So I am also representing my co-authors, Dr. Jessica Chen and Dr. Whitlow Au from University of Hawaii, Hawaii Institute of Marine Biology, and Dr. Peter Dahl and his student Alex Soloway from APL at University of Washington. So we're going to talk about the Pulo Underwater Demolition Range, which is this area here south of Oahu in the main Hawaiian Islands. A lot of talks that we've heard so far to date at the conference have concentrated on the impacts of military sonars in deep water, deep diving odontocetes, but relatively little attention is given to some of the shallow water operations that are done. Rightfully so, it's a smaller component. But this area is utilized by about 4 or 5 different units with special mission requirements to be able to use underwater explosives in the performance of their military duties. And it has more of an impact potentially on coastal habitat and coastal odontocete species. And full disclosure, this is a picture of me blowing something up on the range in 2006. So if you want to talk about bias, that's me. Okay, so what we wanted to do is we wanted to take a look at this area and say, okay, what's the soundscape? What is actually the environment that's out there? And then try to, using passive acoustics, and then try to use passive acoustics to determine if we could hear odontocetes and figure out when they may or may not be actually using that habitat. And then finally collect direct measurements of explosive detonations during training events to find out what disturbance might be going out in the water, and then possibly contextualize all that information and see if it might help with management strategy related to deconflicting the requirement to do the detonation training with the impact on the animals. So the instrument of choice for our passive acoustics were the ecological acoustic recorders, first described by Mark Lammers in 2008. Really, really great tools, versatile tools. And these pictures are of a variety of active duty military doctors from the U.S. Navy and allied navies actually deploying and recovering them over the period of the study. So this is a zoom in of the actual location. This box is marked on the chart, and that's the actual area where the underwater detonation operations occur. Our first instrument was down here on the eastern side of the range over hard bottom and in vicinity of a coral reef type substrate. And the second device was on the western side over here on a relatively flat sandy bottom. And those were the locations that were far enough away that we could still get the recording, or close enough we could still get the recordings, but hopefully far enough away that they weren't actually damaged by a detonation shockwave. So I think things worked out well. We picked a good spot. Okay, so in order to collect our soundscapes, we collected 30-second, duty cycle 30-second files every 5 minutes for about 3 years, and then we looked at the energy levels that were collected and evaluated those on 3 different time scales: a monthly type time scale, a daily time scale, and then an hourly time scale, independently doing the east side and the west side throughout the entire exercise. Throughout the entire course of the study. So just on a gross level, the eastern site that was located closer to hard substrate and coral colonies, much louder than the western site, which was over a softer sand area. And this is just a gross, about an 8 dB difference between the two sites over the course of the study. And then here, the eastern site, it's interesting, when you break it out into frequency bands, it seems pretty uniform and regular, average over a 24-hour period, but the western site, not so much. And if you look, the overall energy level is lower, but the variability is much higher, and there could be a masking effect going on there. This area, I know that we heard a lot more small boats and shipping type noise in that location than at the other location. And then here, this is the hourly breakdown throughout the study cycle. That's that very clear classic diode pattern where it's noisier when it's dark outside, the noise level drops, and then it starts to go back up again toward dusk. Same type pattern in general, but a little bit messier on the western location. So once we did that, basically, there weren't any huge findings that we weren't expecting to find related to the total soundscape, except this was a pretty big difference, possibly related to the snapping shrimp. So then we moved on to the O'Donnell-Seat whistle detection task. So Lammers also described during some of his field research that the animals in this area have a tendency to transit along the 60-foot isobats. So that's where we put our instruments in the hopes of actually being able to hear some of the animals. And the files were analyzed from 8 in the morning to 4 in the afternoon, because that's basically when the range is open for business for training for the 3 years of the study. And we first tried an automated detector. And I don't know if anybody in here has actually tried automated detectors with snapping shrimp, but it didn't work out so well. So then we went to a manual analysis. Over 130,000 files were each listened to by a bunch of graduate and undergraduate researchers. Just to give you an idea of what you're looking at, this is our spectrogram, and this is actually a good file because we could see 2 whistles here. I promised a whole bunch of undergraduates that they would study marine mammals, and then of course I put Jessica Chen in charge, and all they saw was computers. So they never saw a dolphin. Okay, so results. Just on a gross, this is the total number that were collected. 7 times as many were detected on the western location than on the eastern location. Again, that might have something to do with masking or habitat preference. There's really no way to tell, except that we could definitely seem to find a few more files on the western side, a significant amount more. So if you look, this is the overall percentage, and I put these boxes in for the benefit of the people in the back, because nobody could read these graphs until I did that. So the percentage with whistles per month on the eastern location, you can see there's a bump up here in February and again in September. That also holds true for the western location with the larger sample size. There's a bump of whistle detections here in February and again in the August-September timeframe. And then here, this is a per hour breakdown. It seems from the eastern side that there were more detections in the morning, trailed off, and then started to increase as you get to the afternoon. That pattern didn't seem to hold as well on the western location, where we actually had more whistles that we could detect. So all of those data, those were all raw data, all of those were put into a GLM binomial, yes for whistle, no for no whistle. And the location was predictably significant. Time of year was significant. Time of day didn't turn out to be significant, and there were a couple of interactions, month versus hour and location versus hour were significant. But the important thing here is behavioral context is important. Just because an animal isn't whistling doesn't mean it's not there. Okay, so these are whistle detections, not necessarily the animal detections. Okay, so moving on to the other part of the story, explosives as an acute disturbance. This isn't a transducer. When an explosion goes off, it converts a solid block of material to gas at a speed of over 8,000 meters per second. So that's an interesting disturbance. The explosive that's used most often out there on the range is composition C4. The equivalency is about 1.3 pounds, 3-4 pounds relative equivalency to TNT. So all of the math and all the calculations converts it to TNT. And what that means is each one of these blocks is about 1.25 pounds. So it's about 3/4 of a kilogram, which is really good because that means that we can have a precise control over the charge size just by adding or subtracting these individual blocks. So the numbers that we were interested in, this is the NOAA guidance on temporary threshold shift and permanent threshold shift for mid-frequency cetaceans in our area. So again, broken out into sound exposure level and peak sound pressure level as well. So our study site basically involved going to this one detonation point and putting an array out seaward and putting several instruments out along shore to try to record these detonations. Now, this was actually a mission that was tasked by Pacific Fleet to an active duty unit. It's the first time that the Navy has actually been ordered specifically to go out there and blow stuff up just so that it could be listened to, as opposed to just usually going out there and ad hoc collecting information. So it was pretty significant. So the vertical array consists of 9 hydrophones about 900 meters seaward of the collection site. The research boat was anchored. They had a wave buoy and then CTD and got sound seed profile information as well from that location. And then again, the same guys who were setting up the charges, the same active duty guys, deployed and recovered the loggerheads, the instruments along the seaward side. So this is what an initiation system looks like if you're not familiar with blowing stuff up underwater. But basically, there's a charge underwater that's connected by a detonating cord. And all of this is explosive. That shock initiates the main charge. And the initiating system is on the top. Those are the blasting caps and the command detonation. Okay, so this is the part that we can vary. So we did 9 shots, 3 replicates, 5 pounds, 10 pounds, and 20 pounds in order to give a precise net explosive weight for the physicists to measure. So this is an interesting graph because here are the shots of all of the different net explosive weights, and this line basically represents the line that accounts for the charge size in sound transmission. This is the Puuloa data in Hawaii, and this dashed line is interesting because that represents the previous work at other ranges that was similar but not necessarily the structure of an experiment. So that's up to a 30 dB difference in peak sound pressure level. And then we saw the same thing when we came to sound exposure level. So again, you had a very, very big difference. What I do want to point out on this is this model only has 2 variables, which is the net explosive weight of the charge in kilograms converted to TNT, and then a range in meters. Okay? This equation is very, very similar to the one that the spec ops guys use when they do their calculations for the underwater detonation. So this is not something that the military guys would be unfamiliar with in order to do their actual detonation planning. So why was there this giant difference between the 2 measurements, between all the other empirical measurements at all the other sites and then what we had in Hawaii? Short answer is we don't know. Rampant speculation is this is the plume from where the surface initiation went down, transmitted the shock wave down. This right here, this little steam cauldron, that basically represents the upper part of the gas globe as it bounces against the surface and then comes back down. That's a lot of energy loss. So that could be one potential reason. So in summary, we had the soundscapes that were collected. What I wanted to do is be able to tell the Navy, hey, if you blow stuff up in February at 10 o'clock in the morning, that's the least likely chance that you're going to run into a dolphin. In other words, to temporarily separate those things. Couldn't necessarily make those conclusions. But down here it shows a lot of promise to be able to spatially separate those. Because the guys out there who are actually doing this will be very familiar with that equation, it's possible to say, hey, if I'm only blowing up a 2-pound charge, this is my exclusion distance. Okay, which means I can monitor that better than if I had to be way out here. So that's one of the things that possibly has some potential for future mitigation possibility and allows them to continue the training that they need to do. So I'd like to acknowledge all of my funders, specifically Pac Fleet Julia Rivers, Sean Hanser at NAVFAC, ONR, officers and men of Mobile Diving Salvage Unit 1, particularly Lieutenant Chris Price, and then OSI and everybody from HIMB. I'd also like to dedicate this to Dr. Eugenie Clark, who got me into marine biology, and all the guys I've served with who have given their lives so that we can study science and peace. So now here are your dolphins. And if you want to find me afterwards, I know that was a lot of material. I'll be happy to answer any questions afterwards.
That's right, people have to.
Okay.